In this video we will run the OpenCL version of the sample rate converter using the ALSA utility aplay. The first thing we'll look at is the ALSA control file, which is in the home directory of the user, and it's the file .asoundrc. This is the file that specifies to ALSA that we are going to use. If we look at the structure pcm.rateconvert in this file, we can see that we've specified an output sample rate of 48 kHz compared to the input sample rate of 44.1 kHz, and that we've told it to use the speaks rate converter. This is the one which has the OpenCL enhancements. We start the application with the command line aplay -d-rate-convert, which specifies that it's the speaks rate converter that we're wanting to use that we have defined in that .asoundrc file. And then we give it an output file. Within the package there is a 1 kHz sine test tone which runs for 5 seconds. This is the file we're going to play in the 1 kHz 5 second stereo.wav file. At this point we need to note that you need to have a USB audio device inserted in the BeagleBone in the USB port, otherwise you'll get an error that the audio device is not found. When you run this application, you should hear on a pair of headphones the 1 kHz tone, but probably for analysis point of view the more interesting information is what's shown on the screen in the logging. So if we look through the logging information line by line, we can see that we have successfully opened the libopencl shared object, and then we have a series of defines. These are the defines that are passed into the kernel.cl file by the application at runtime. In this case we have increased the input sample rate buffer from the default 160 samples to 1600 samples. This is because we can get the benefit of OpenCL when we have a much larger buffer size, which gives us more processing, and so the amount of processing relative to the overhead of the OpenCL is significantly higher. Because we're increasing the sample rate from 44.1 to 48 kHz, the actual output buffer size is 1742, which is the ratio of 48 to 44.1. The next couple of lines are internal to the sample rate converter, so the filter length and the sync table lengths that are being used. Finally, when we run, we have two sets of timings. The first line, which is create 710 microseconds, set arg 27 microseconds, run kernel 11,027 microseconds, read buffer 86 and release 25. These are the timings of the individual steps within the OpenCL kernel. So as a kind of an approximate summary, the kernel is running for 11 milliseconds and there's approximately 1 millisecond of overhead to create the buffers and then release them afterwards. The next line, buffer creation, process and buffer release, are looking at the timings from the application point of view. So the process in the middle of 12,000 microseconds is the sum of the total OpenCL timing requirements. The timings before and after are those at the application side to create and manage the cache, which is 1.38 milliseconds, and then to release a further 900 microseconds. So this is giving us the total timing for the system, and these are the numbers that are used in the report to analyse the total system loads.